Okay, welcome everybody to our first talk in the morning session. Very excited to hear from Lauren Williams from Harvard University, who's going to be telling us about combinatorics and geometry of the Amplituhedrons.
So thank you so much, Federico, and big thank you to the organizers for putting on this wonderful workshop and for inviting me to speak. I will be telling you about joint work with a number of co-authors, Haim Evan-Zohar, Stephen Karp, Svika Lecrec, Matteo Parisi, who is here, I believe, yes, and is on the job market this year, so look out for his file, Melissa Sherman-Bennett, Ron Tesler, and Yan Zheng. So I decided I should pitch my talk at the sort of typical participant of the combinatorial algebraic geometry program. So I want this talk to be sort of very friendly to people who are not necessarily experts in amplitudes and who maybe haven't seen this kind of stuff before. So I'll start by giving an introduction to what is the positive Grassmannian, just a little bit about scattering amplitudes and the role of the amplituhedron. I'll explain how, in order to understand the amplituhedron, we triangulate or tile it. Then I'll tell about the connection to cluster algebras, as has been mentioned by a few speakers earlier, Anastasia and also Laura. And then I'll tell you about some kind of beautiful numerical conjecture, the magic number conjecture. And along the way, we'll see connections to different interesting objects from combinatorics. So please, by the way, feel free to interrupt if you have any questions. So just a review of my notation. The Grassmannian is GRKN, is the space of k-dimensional subspaces of an n-dimensional vector space. And we represent elements of the Grassmannian by full rank k by n matrices. So the row span of such a matrix gives a sorry, I don't know why the pointer stopped working. The scroll forward and backward is no longer working. Actually, the computer seems to be a bit frozen. Okay, thank you. Okay, all right, so given a capital I, a k-element subset of 1 through n, the Plücker coordinate P sub I is the minor of the k by k submatrix of C located in columns I. And now associated to this data of a matrix, together with its Plücker coordinates, we can associate a matroid. What is that matroid? We can think of it as just the collection of k-element subsets of 1 through n, where the Plücker coordinate is non-zero. So another way to say that is our matrix gives us a list of column vectors, and we're just going to record the data of which collections are linearly independent or not. So Gelfand, Goreski, McPherson, and Serganova introduced the matroid stratification of the Grassmannian, which is defined as follows. So given a collection of k-element subsets of 1 through n, we let S sub m be the subset of the Grassmannian, where the Plücker coordinate P sub I is non-zero if and only if I belongs to that collection. And this gives us a way to stratify the Grassmannian into these matroid strata. But a famous result of Minyoff tells us that the topology of these strata is terrible. So they can be as bad as that of any algebraic variety. Okay, so now this leads me to the notion of positive Grassmannian. So somehow if you start with this terrible matrix stratification, but you throw in an extra adjective positive, everything becomes beautiful. So the background, so this goes back to Lustig's work in '94 on total positivity for flat varieties, subsequent work of Reach, and Postnikov's very influential 2006 preprint on the positive Grassmannian. So we will define the positive Grassmannian to be the subset of the real Grassmannian where Plücker coordinates are always non-negative. And inspired by this matroid stratification, we can partition this positive Grassmannian into pieces based on which Pluker coordinates are strictly positive and which are 0. And so let's do the same thing we did before. Take your favorite collection of K element subsets of 1 through n, and let's let S sub m be the subset now of the positive Grassmannian, where your Pluker coordinate is positive if and only if I belongs to that collection. And now in contrast to the terrible topology of matroid strata, if this subset Sm is non-empty, then it's actually a topological cell called a positroid cell. It's homeomorphic to an open ball. And so we get this beautiful positroid cell decomposition of the positive Grassmannian. And Postnikov's work in 2006, a big piece of it was classifying the cells and showing that they were in bijection with various combinatorial objects. Okay, so let me just mention a few ways in which the positive Grassmannian has come up in sort of quote unquote real life phenomenon. So back in 2006, it was a surprise to me when with work with Sylvie Cortil, we made a link between the combinatorics of cells of the positive Grassmannian and the stationary distribution of the asymmetric simple exclusion process. This is a model from statistical mechanics in which particles hop and repel each other on a one-dimensional lattice. And for some reason, the probabilities can be encoded very compactly using the combinatorics of cells. In a different direction, in work we did with Yuji Kodama, we found that the cell structure of the positive Grassmannian allowed us to explain the interaction patterns of regular soliton solutions to the KP equation. So if you're familiar with Playbit graphs and on-shell diagrams, roughly speaking, the interaction patterns that one sees in shallow water waves look like what you see in Playbit graphs. And then what's most relevant to my talk today began in this work in 2012 of Nima, Jake, Freddie Cachazo, Goncharoff, Postnikov, and Trinka, in which they explained that you can use the positive Grassmannian to compute scattering amplitudes in n equals 4 super Yang mills. So this is scattering of elementary particles. And for those of you who are not physicists, in quantum physics, the scattering amplitude is a probability amplitude that describes what happens when some particles with given momenta collide. And this quantity is the fundamental quantity of interest in scattering experiments like at the Large Hadron Collider. They can be computed in different quantum field theories, and the one relevant to today's talk and to the Amplituhedron is called n equals 4 super Yang mills. Okay, so this is my all I'm going to say, almost all I'm going to say about physics. Okay, so we saw a bit about the Amplituhedron in Simone's talk. I will define the same object. So this is the tree Amplituhedron, and it was defined by Arkani Hamid and Trinka in 2013. So how does this go? We fix positive numbers n, k, and m with k plus m at most n. And then we let Z be a tall, skinny n by k plus m matrix with maximal minors positive. And we let Z tilde be the map from the positive Grassmannian of k planes and n space to the related Grassmannian of k planes and k plus m space, which is simply induced by matrix multiplication. So we start with our matrix C lying in this positive Grassmannian, well, I should say representing a point in this positive Grassmannian, and we look at C times Z, that's a k by k plus m matrix. So it spans a k space and k dimensional subspace of k plus m dimensional vector space. And then one can check that, well, sorry, I should have said C times Z, you can check, has full rank k. And so it gives rise to an element in this Grassmannian. And then the Amplituhedron is defined to be the image of the positive Grassmannian under this map. So it's a subset of the Grassmannian of k planes and k plus m space, and it's full dimensional. So it has dimension k times m. Okay, so what was the motivation for this object? So back in 2005, there was a very important recurrence of Brito, Cachazo, Fang, and Witten expressing scattering amplitudes as sums of rational functions of momenta. So, so they gave a recursion, which gave this expression for scattering amplitudes as a sum of terms, and each individual term in general had spurious poles, so singularities that were not present in the final amplitude, in the final answer. And based on some small examples, Hodges pointed out that in some cases, the amplitude can be seen to be the volume of a polytope. And the spurious poles arise from the internal boundaries of the triangulation. So basically, Hodges gave an interpretation to the recurrence where every term corresponded to some simplex in the triangulation of this polytope. And the spurious poles were attached to internal boundaries in the triangulations that were not on the exterior of the polytope. And so he asked, in general, can we see the amplitude as the volume of some geometric object? And so that was the question that Arkani Hamed and Trinka answered when they discovered the amplituhedron. And in this setup, the BCFW recurrence gets interpreted as a quote-unquote triangulation or tiling of the m=4 amplituhedron. Okay, so the amplituhedron makes sense for any m, as long as k plus m is at most n, but the one of most interest to physics was this m=4 case. Okay, so this is just a review of the definition. So like I said, this is defined for any m, but most relevant for physics when m=4. And m=2 also has connections to physics. Okay, any questions? Okay, so let me point out that that mathematically the amplituhedron generalizes a number of interesting objects. So first, if m is n minus k, then this matrix Z is just an invertible matrix, and so you can think of the amplituhedron as just recovering the positive Grassmannian. Okay, so it's a little bit boring, but it's saying that you can think of the amplituhedron as a generalization of the positive Grassmannian. Now, when k is 1 and m is 2, the amplituhedron is equivalent to a polygon in RP2. So let me say a word about why that's true. So we have our Z matrix. This is our n by k plus m matrix. So here it's an n by 3 matrix with maximal minors positive. So let's label the rows, Z1 through Zn. So these are 3 vectors. The fact that the minors of this matrix are positive means that Z1 through Zn can be thought of as the vertices of a polygon in RP2. And they're going around cyclically because of the positivity. And now the map Z tilde is mapping the positive Grassmannian of one plane in n space to GR1, 3. And it's sending our tuple, C1 through Cn, of non-negative numbers to this linear combination of Zi's. And then as the Ci's range over all non-negative reals, we get points, all points of this polygon. So that's what happens when k is 1 and m is 2. And I'll point out that if k is 1 and m is general, then we get not a polygon anymore, but a cyclic polytope. And the fact that our totally positive matrix gives us the geometry of the cyclic polytope was actually something pointed out, I believe, in Bernd's master's thesis from 1988. Okay. Another nice example, if m is 1, then the amplituhedron is contained in the Grassmannian of k-planes and k plus m space, so k-planes and k plus 1 space. And this turns out to be homeomorphic to the bounded complex of a cyclic hyperplane arrangement in RK. So that was something that we studied in a paper with Stephen Karpin in 2016 or 17. And I should say, when Stephen and I started looking at the amplituhedron, we first tried to understand m=4. We quickly realized that was too hard. Then we looked at m=2. We decided that that was hard too. So we went to m equals 1 and we started to make some progress. So small examples are good. And I also wanted to advertise that there's some beautiful work of Mandelstam, Pavlov, and Pratt, which looks at some extensions of this where you relax the conditions on your matrix Z. Okay, so now how can we understand the amplituhedron? So we want to understand the volume of it. So we need to triangulate it, or more precisely, tile it. Now the amplituhedron is not a polytope. It's the image of the positive Grassmannian under this map. The positive Grassmannian is not a polytope. The amplituhedron is definitely not a polytope. So we need to find the right notion of tile and tiling. Okay, so this again is just a reminder of the definition of amplituhedron. And as I mentioned before, the amplituhedron is full dimensional in the Grassmannian of K planes and K plus M space. So in particular, it has dimension K times M. And we have a cell decomposition of the positive Grassmannian, which we completely understand. And the amplituhedron is the image of the positive Grassmannian. So what we want to do is understand the amplituhedron using images of cells of the positive Grassmannian. So that's going to be the goal. So this positive Grassmannian in general has dimension much larger than the amplituhedron. So what we would like to do is restrict our attention to correct dimensional cells of the positive Grassmannian. We're going to focus on K times M dimensional cells of the positive Grassmannian, and in particular, such cells where we can prove that this map Z tilde is injective. So we'll define a tile of the amplituhedron to be the image of a Km dimensional cell here, such that Z tilde is injective on that cell. So this notion of tile, this is going to be our analog of like a simplex in a triangulation. And then a tiling is going to be a collection of tiles which fit together in a non-overlapping way to cover the amplituhedron. Question?
If I take a larger cell, does it map to a tile?
So it may or it may not. It could be a union of tiles. Yeah. Okay. So so what can we say about tiles? So for m equals 1, we classified them. The total number is n plus k minus 1, choose 2k. For m equals 2, we also classified the tiles. So we're classifying all of the 2k dimensional cells which map injectively. And that number of tiles is also a nice combinatorial number. It's this sequence in Sloan, and it's a refinement of the Schroeder numbers. For m equals 4, we do not know a classification of tiles, but we know a lot of them. And in particular, all ways of iterating the BCFW recurrence gives collections of tiles. Okay, so now one thing that we would really like to understand is how to cut tiles out of the amplituhedron. So we want to understand something like facet inequalities. And in order to do so, we need good coordinates, right? So far, we've just defined the amplituhedron to be the image of the positive Grassmannian under a certain map. But we'd really like to have appropriate coordinates on this side in order to talk about the amplituhedron and to talk about tiles. And you might think that you want to use Plücker coordinates on the right-hand side, but that's actually a very bad choice. We want coordinates that somehow take into account our choice of the matrix Z. Okay, so what are the coordinates we're going to use? They're called Twistor coordinates, and they're very simple to describe. Okay, so as before, so Z is an n by k plus m matrix, and we'll let its rows be denoted Z1 through Zn. And now let's take an element y in the Grassmannian of k planes and k plus m space. And I'm thinking of this, we're always taking matrix representatives. So now if I is an m-element subset of the numbers 1 through n, we will define the twistor coordinate z sub I of y to be the determinant of the following matrix. So take y, that's a k by k plus m matrix. And now let's take the rows of z corresponding to this m-element subset and stack them below y. So now we're going to have a k plus m by k plus m matrix, and we can take the determinant. And that's called the twistor coordinate. And these first came up in a paper of Arkani Hamed, Hugh Thomas, and Jaroslav Trinka. So these are very good coordinates, and actually they're more familiar maybe than they look because they can be identified with Plücker coordinates on a related Grassmannian of m planes in n space. Okay, but anyway, just the important thing to keep in mind is that these are coordinates on this Grassmannian, and they are indexed by m element subsets of 1 through n. Okay, any questions? Okay, so let me tell you what tiles look like, and we'll start with some simplest kind of example. So this is an m equals 1 picture. So for m equals 1, I told you that amplituhedron is the bounded complex of a hyperplane arrangement. So here we've taken n equals 5 and k is 2. And so what you see here is 5 hyperplanes in 2-dimensional space. These hyperplanes are specified by the rows of our matrix Z. And because of the positivity of Z, these hyperplanes are sort of cyclically arranged. And now, and then I said the amplituhedron is the bounded complex of this arrangement. So the amplituhedron is just the union of all of these bounded regions. And it turns out that this partitioning into the bounded chambers is exactly a tiling of the amplituhedron. So in particular, each of these bounded regions is the image of a cell in the positive Grassmannian. And I'm labeling the bounded regions by signs based on which sign of each hyperplane they're on. And here, our twistor coordinates exactly are telling us where we are with respect to these hyperplanes. So for example, if you take this tile here, then its facet inequalities are the twistor coordinate z5 is non-negative. So here's the line L5, and this is saying that we are on this side of the 5th hyperplane. Z4 is non-positive. Here's Z4, so we're on the left side of that hyperplane, and Z3 is non-negative, so we're above this hyperplane. So these are the facet inequalities for this particular tile. And for m equals 1, just like for polytopes, the boundaries of these tiles are linear. Any questions? Okay, so now let's do an m equals 2 example. Now this is a little harder to imagine because here our amplituhedron has dimension 2 times k. Here k is 2. So this small example A522 is a 4-dimensional object. Okay, so I can't really draw a 4-dimensional object, so you have to imagine. But this is a 4-dimensional blob, which has a tiling into three tiles. And I'll tell you exactly what those tiles are. So again, my twistor coordinates are Zij. They're indexed by m element subsets of 1 through n. So the first tile is given by these inequalities on twistor coordinates. And one mnemonic that you can use to write down those inequalities is to draw this kind of bicolored subdivision of a pentagon. And this gray region here is telling us about that Z13 is non-negative, and Z34 is Z45, and Z15. These are the boundaries of this tile. And we also have to specify that Z14 is negative. And then there's a second tile, which has a similar list of inequalities and is associated to this picture. And then the third tile has these inequalities associated to this picture. And in all cases, the facets of the tile are associated to the sort of boundaries of these gray polygons here. But now, so already we see in this example, and in general for m at least 2, the boundaries of tiles are no longer linear. These Twistor coordinates are not linear. You know, these are like Pluker coordinates in G2n. So they're not linear. But the very interesting feature is that they are described by compatible cluster variables for the cluster structure on GRM, n.
Why are some of those bold and not bold?
So I bolded them to show boundaries between tiles. So you know, our tiles are 3 4-dimensional pieces. So you shouldn't think that this is a picture of the tile because this is 2-dimensional, not 4-dimensional, but it's just a mnemonic. But this first tile has the inequality Z14 less than 0. Oh, sorry, let me go to this one. So these two tiles share the boundary Z13, but they're on opposite sides. And then these two tiles share the boundary Z14, but they're on opposite sides. So I bolded those to show, so you can see how they're on opposite sides of some curve. Okay, but now the really interesting feature when m is at least 2 is that boundaries of tiles can be described by compatible cluster variables for the cluster structure on GRM, n. So yes, so I want to back up a little bit and say a little bit about cluster algebras and their connection to this story. So this connection goes back a number of years. So it was already discovered a connection between cluster algebras and scattering amplitudes by physicists. What they had observed is that when you calculate the scattering amplitudes as rational functions of momenta, the poles arising in the expressions seem to be related to compatible collections of cluster variables. And they called this cluster adjacency. And so this cluster adjacency phenomenon was first found in work of Drummond, Foster, and Gertigan, and then Golden, McLeod, Spradlin, and Volovich, and then reformulated in an Amplituhedron way for m equals 2 by Lukowski, Parisi, Spradlin, and Volovich. This is my cartoon image of a physicist. So yeah, so before I say more details on this connection, I want to review the notion of cluster algebra. So we did see them a little bit in Anastasia and Laura's talks, but I don't want to necessarily assume that you have digested it. So just to give the overview, cluster algebras were discovered by Fomin and Zelvinsky in 2000. And they're a class of commutative rings with a kind of remarkable combinatorial structure. They come with distinguished generators called cluster variables, and the relations are encoded by quivers and quiver mutation. So that's a kind of algebraic framework, but there's also a more geometric point of view initiated by Fott-Gontchoff, in which they defined cluster varieties to be some varieties whose coordinate rings are cluster algebras. And these varieties come with many nice torus charts. So you can think of cluster variety as a kind of generalization of toric variety. And the coordinate functions on a given torus are called compatible cluster variables. So many well-known varieties have cluster structures. And it's quite useful to find a cluster structure because there's many general results about them. And then most relevant to this talk is the fact that the coordinate ring of the Grassmannian has a cluster structure. So meaning the Grassmannian has many nice torus charts and their coordinate functions are cluster variables. Okay, so I'll just sort of give you the example that almost everyone starts with. which is about the cluster structure on the Grassmannian of two planes in n space. So if you want to think about the cluster structure on G2n, then this is encoded by triangulations of a polygon. So we have one cluster torus for each triangulation. So here's a triangulation of an 8-gon. So this is going to have to do with G28. And I've labeled my sides and my diagonals by Plücker coordinates corresponding to the endpoints of each side and diagonal. And the fact that we have a cluster torus for each triangulation means in particular that the Plücker coordinates you see here are algebraically independent, and they generate the ring of rational functions on the Grassmannian. Okay, but just one thing I'll point out is that two Plücker coordinates are what's called compatible, meaning they can lie in the same cluster, if and only if they label two non-crossing diagonals. Okay, so the picture for G2n is very simple, but if k is bigger than 2, the cluster structure becomes incredibly complicated. There are infinitely many cluster variables in general. The cluster variables include all Plücker coordinates, but they also include high-degree polynomials in Plücker coordinates as well. And the cluster variables are just simply not understood in general. Okay, so now let me tell you what these cluster algebras have to do with tiles and the Amplituhedron. So this is just a review of my notation and the notion of Twistor coordinate. And remember, the Twistor coordinates are indexed by m element subsets of 1 through n. Okay, so here's a very general conjecture, which is a generalization of earlier conjectures, including the one that was for m equals 2. But we believe this is true for arbitrary m, arbitrary n, k, and m. Okay, so let's start with an arbitrary tile of the Amplituhedron, a, n, k, m. Then every facet of the tile is, I'm putting in quotes, cut out by a cluster variable for the Grassmannian of m planes in n space. And now what do I mean by cut out by a cluster variable? Let me just make that a little more precise. What we're saying here is that if you take a facet of the tile, well, this is going to be cut out by a polynomial in Twistor coordinates. But if you just take every Twistor coordinate, which remember was indexed by an ML element subset of 1 through n, and replace that Twistor coordinate by the Plücker coordinate, then the statement is that that polynomial in Plücker coordinates is a cluster variable for the Grassmannian. Okay, is it clear what I mean here? Okay, the second statement is that these facet polynomials, so if you start with one tile and you look at all of its facets and you look at all the associated cluster variables cutting out the facets, then the statement is that these polynomials are compatible cluster variables. So this is a very, very strong statement. And I don't know, it says, for example, that the number of facets is bounded by m times n minus m, say. And then the third statement is that our tile should be described by specifying that certain cluster variables are positive and certain are negative. So in cluster algebras, we're very familiar with defining positivity. Oh, sorry, there's a question? For any m, including odd. Including odd. Uh-huh.
So there's a finite list of cluster variables involved in this case.
Only when
m and n are all parameters are fixed.
No, because for example, for the Grassmannian of 4 planes in 8 space, there are infinitely many cluster variables.
I understand, but in this description of all the types, there's a finite.
Oh, yes.
Do you know a priori how many, or?
No, but we'd really.
In some sense, one could argue those are the only relevant clusters.
That's right. So yeah, so we would really like to know, but we don't know. Yeah. Mm-hmm.
So this is only for individual tiles, or if you have a tiling, do you have any conjectures for how the different
No, so we don't understand, yeah, so it's not like, yeah, there's not a clear relationship between the cluster structures, even on two adjacent tiles. That's not obvious. Yeah. Yeah. Uh-huh.
In the first part, if I'm very Z, how does the
So that's a great question. So of course, the amplituhedron depends on Z, but what is really essential about these twistor coordinates is that the twistor coordinates have the dependence on Z built in. And so if we vary Z, the statement shouldn't change. The description of facets, all of that, nothing should change. Yeah. So you know, if I take two different Z's, I'm going to get the same list of cluster variables. Yeah, so I'll just mention that in cluster algebras, we're very familiar with the idea of defining the positive part of a cluster variety as the subset where cluster variables are all positive. But here we see a kind of different phenomenon where some of them are positive and some are negative, but the signs are fixed. Okay, all right, so what can we say towards this conjecture? So it's true for m equals 2. Every tile for the m equals 2 amplituhedron can be described by inequalities, zi of y being plus or minus, being positive or negative, where I ranges over some non-crossing diagonals of an n-gon. So in other words, the boundaries of a tile are cut out by compatible cluster variables. Okay, so the first step in proving this theorem was we had to classify every single tile so that we would be able to check it was true. So we can see already in this example that cluster adjacency holds. The list of, so if you sort of squint and turn these z's into p's and think of these as Plücker coordinates, then this list of Plücker coordinates is all compatible. And similarly, these are all compatible and these are all compatible. Okay, now for m equals 4, we have a large supply of tiles. So for m equals 4 and fixed n and k, the BCFW recurrence produces many what you might call BCFW cells of the positive Grassmannian, whose images were conjectured by Arcani, Hammond, and Trinka to be tiles for the amplituhedron. So this gave a lot of conjectural tiles. Oh, sorry, and I should say, I'm not really going to give details about the BCFW recurrence, but if you're familiar with on-shell graphs or playback graphs, there's a kind of graphical way to build these cells. I almost fell off the stage, but I seem to have recovered. Okay, so there's a graphical way to build these cells. And just to sort of give you a taste of how many there are, when k is 2 and n is 9, 10, 11, there's this many BCFW tiles. So anyway, yes, so this is just a number of tiles. Yeah. Okay. Okay, so we showed that all of these BCFW cells give rise to tiles of the amplituhedron. So each one does map injectively. And we also showed that the boundaries of each such tile is always cut out by compatible cluster variables. So we checked cluster adjacency is always true for the BCFW tiles. And in particular, every tile is described by specifying that certain cluster variables are positive and certain are negative. And I should say that for m equals 4, it's significantly harder than m equals 2, because in general, these cluster variables are high-degree polynomials in Plücker coordinates. And so, we don't know all of these, all the cluster variables for GR m, n. And so we had to kind of prove this inductively using the inductive structure of BCFW cells. Any questions? Uh-huh. Yeah, so so they can be arbitrarily high degree dependent on n and k. Yeah, I forget exactly. Like there's a polynomial bound in N and K. Other questions? Uh-huh.
This was something very basic. So when you say to classify the tiles, do you mean a tile with potentially more confining
Right. So by tile, I only mean that it is the injective image of a cell of appropriate dimension from the positive Grassmannian. So it has the potential to be part of a tiling. In theory, it may not be. All of these BCFW cells do take part in tilings. There's other tiles that we know about, like there's a tile called the Spurion tile, and there are tilings that involve that as well. So there's also many tilings that are not BCFW tilings, that are not just using BCFW cells. Yes, that's all. Just on when is the map injective on this m times k dimensional cell. Other questions? Okay. All right. So that leads us to the discussion of tilings, because so far we only discussed tiles. So then the question is, can we fit some tiles together to tile or triangulate the amplituhedron? And remember, we defined a tiling to be a collection of tiles such that their union equals the amplituhedron and the interiors are pairwise disjoint. Okay, so what can we say about these? So for m equals 2, in some sense, we have a classification of the tilings of the amplituhedron. So what we showed with Parisi and Sherman-Bennett is that the tilings of the m equals 2 amplituhedron are in bijection with what you might call moment map tilings of the hypersimplex. So anyway, so in some sense, we have a classification of tilings for m equals 2. Although we don't know, if you just give me a collection of tiles, I don't have a simple combinatorial recipe to say offhand whether or not that's a tiling or not. And then for m equals 4, Arcani, Hammond, and Trinka conjectured that certain BCFW collections give tilings of the amplituhedron. And I should say there's many of these. So if you fix n and k, there's many of these BCFW collections, but there's also a sort of standard collection obtained by running the BCFW recurrence in the standard way. And there was this beautiful work by Evans, Zohar, Leclerc, and Tesler, where they showed that for each n and k, the standard BCFW collection gives a tiling of the amplituhedron. And then in joint work with them, we showed that every way of running the BCFW recurrence, so every BCFW collection gives a tiling of the amplituhedron. As Jake was pointing out a moment ago, there's many of these BCFW collections, hence many BCFW tilings. And just to give an example, if n is 8 and k is 2, there are 2,624 BCFW tilings, and then one of these is the standard one.
So there was argument which is probably not correct, is that so basically non-standard BCFW recurrence are obtained by kind of twisting and rotating each piece in an observable way.
But it sort of yeah, so that's a great question. So this is a picture of the BCFW recurrence. And so when you build a BCFW cell, you're starting with two smaller BCFW cells and putting them together. But when you build up, a large BCFW cell, you've applied this operation maybe many times. And at every stage, you can do a cyclic shift on either component.
Each piece, small Grassmannians,
Mm-hmm. Mm-hmm.
get another tiling. Just obviously because it's inherent under the shift and keep combining. In this case, you get a lot of tiling. So maybe something is wrong here.
No, you definitely won't get. I mean, we have to do this rotation in all these sort of smaller pieces along the way. But I guess another simple thing I can point out is that one ingredient was showing. So one ingredient in showing a tiling statement is showing that all of the BCFW cells map injectively, and so they had only done it for a very specific collection of BCFW cells, and their arguments didn't extend to show that the Amplituhedron map is injective on the other BCFW cells. So that's one thing I can point out. So there were. Mhm. Sure. But the point is, when you build up these cells, you've done a whole bunch of operations. You've applied this recurrence 50 times, and every time you do the recurrence, you have different choices of rotate or reflect or whatever. So it doesn't follow easily, and in fact, we had to use a very special choice of coordinates to control the injectivity, and it was cluster coordinates. But I'm happy to talk more afterwards.
BCFW cells surely aren't the only ones that are injective, like spurion.
That's right. Yeah, so we understand some more general mechanisms for injectivity, but we don't have a complete understanding yet. Okay, yeah, so I'm not really going to talk about the proof, but just a key idea is that this connection to cluster variables is really essential. Also for showing disjointness as well. Okay, so let's go back to combinatorics. So the numerology of tilings is very interesting. So a while ago, with Stephen and Jan, we assembled all the numerology of tilings that we had available, and so we were just looking at N, K, and M, and the question we were asking was, for a tiling of the amplituhedron, how many tiles are in that tiling? Okay, we're just saying, take any known tiling or conjectured tiling, how many tiles are in that tiling? And we assembled this list of numbers, most of which were conjectural at the time. And we were trying to, so we have binomial coefficients here, and we have Neriana numbers here, and we were trying to say, okay, well, what's the number that might generalize all of these? So we made this observation. So let M of ABC be this interesting number. And what we observed was that every number in that table, so all the known tilings of the amplituhedron for even M have the cardinality, this number, this function of k n minus k minus m and m over 2. So we call this prediction that the size of a tiling is this number, the magic number conjecture. This number, by the way, is a very old famous number, originally studied by Major Percy McMahon in, I don't know, maybe late 1800s or something. And something very interesting about this sort of conjecture is that there's this symmetry. So A, B, and C are there's no, there's a symmetry in A, B, and C here. So there's this prediction would suggest a symmetry in k, n minus k minus m, and m over 2. And I'll just mention that the symmetry between k and n minus k minus m is something called parity duality, which was, I think, discovered by physicists and then proved by Pasha and Thomas. And that's the symmetry between these first two numbers. Okay, and the combinatorial. Yes. So the symmetries would be generated by 2. And I think it's a fluke. I think it's a fluke if you look at another symmetry, I think it's an accident, this numerological coincidence. I mean, we looked a little, say it again? Usually what?
Don't believe that something like this is something like this can be accidental.
Yeah, well, yeah, maybe not accidental. Maybe that's the wrong word. But we don't see like a bijection between tilings that would swap two other parameters. Yeah. Yeah, but yeah, anyway, it's quite mysterious. Okay, and then combinatorially, this number, I should say, counts different combinatorial objects, non-crossing lattice paths, plane partitions, rhombic tilings, perfect matchings. So it's a very nice number for combinatorics. Okay. So I'll just end with this last statement that we can prove this for m equals 2. No. I mean, it's not. I mean, it's like for large m, we don't even know of tilings or how to generate tilings. So yeah. So anyway, so yeah. So lots of things. Yeah. So it's it's kind of a wild conjecture, but it's true for m equals 2. So the statement, so this magic number for m equals 2 is just the binomial coefficient n minus 2 choose k. Sanity check. If you specify that k is 1, then your amplituhedron becomes an n-gon, and this statement says that all tilings of an n-gon have size n minus 2, which is true. Triangulations of an n-gon have size n minus 2. Okay, so I can give you the idea of the proof, which in theory one could try to mimic for higher m, but would be, I mean, is hard. So, okay, so step 1, we classified all tiles for the m equals 2 amplituhedron. So this was a kind of essential step in the proof. Now, if you have a classification of tiles, and if you have a way to associate an additive invariant to every tile and to the amplituhedron, which is constant on each tile, then this would show that the volume of each tiling is the same. Right. So if you were trying to do something like this for some class of polytopes, and if you showed that like the volumes of all your potential simplices were the same, this would show that all your tilings would have the same size. Okay, so then we need to find the appropriate additive invariant to every tile. Now this m equals 2 amplituhedron is naturally decomposed into Eulerian many W chambers labeled by permutations with k descents. So this is very much an analog of the statement that the hypersimplex has a triangulation, a unimodular triangulation into simplices, into Eulerian many simplices labeled by permutations. This is like a very, very, very precise analog of that statement. And then we define a Park-Taylor function for every tile. And the way we do that is we see that every tile is decomposed into some chambers labeled by permutations. We have to classify which chambers it's decomposed into, and then we sum up the Park-Taylor factors for each of its W chambers. I can say more later if anybody wants to know, but this Park-Taylor function is the same Park-Taylor function we saw in several other talks. And then we show that this Park-Taylor function associated to every tile is the same for each tile. And the fact that this quantity is invariant is very related to a paper of Arcani-Hamed, Borgelli, Cacciazzo, Postnikov, and Trinka. It's very, very related to their paper on non-planar G2N Playback graphs. Okay, but anyway, so once we've defined this additive invariant and shown it's constant on every tile, it follows that every tiling has the same size. And there's one tile we understand very well, and it has n minus 2 choose k. Okay. Yeah.
form? Like, do they sum up the domain form or something?
Yeah, so it's different from that. So it's a little weird. It's a little weird, yeah. Okay, right. So as I mentioned, this conjecture is proof for m equals 2, and it's also holds for k equals 1 because that's the cyclic polytope case. And then I just mentioned this conjecture is kind of striking because almost no polytopes have the property that all triangulations have the same size. The only examples, as far as I'm aware, are even dimensional cyclic polytopes. Okay, yeah, so just as a summary, the Amplituhedron includes as special cases many interesting objects, the positive Grassmannian, cyclic polytopes, the bounded complex of cyclic hyperplane arrangements. And while the Amplituhedron is not a polytope, we can make an analogy with polytopes and study triangulations, tilings, facets. And then we get these beautiful connections to cluster algebras and enumerative combinatorics. So I will stop there, and here's some references.
Any questions for Lauren?
Yes, can you explain for this magic number conjecture if there are like any ideas on how to do this with the bijective proof? Is there some idea on how to associate like one of these combinatorial objects that you listed to the tiles?
Oh, yeah. Yeah, so for m equals 2, we showed that tiles are in bijection with these bicolored subdivisions, which are these kinds of tilings of an n-gon by black and white polygons. But we don't have a good understanding in general of when a collection of those would form a tiling. We don't have a good combinatorial understanding of that. But there's something else one could try to do, which is look at flips for tilings and then try to show that the space of all tilings is flip connected. So that would be another approach. But we also don't know how to do that.
Question is, I think I said this before, so tilings are kind of analogs of triangulations, but usually for triangulations, people require stronger property that two tiles not just color things, but intersect properly.
Yeah, that's right.
As far as I understand, in general, BCFW tilings don't satisfy this property.
That's right. That's right. So the kind of standard way of running BCFW recurrence does give rise to something with nice intersections on the boundary. But in general, if you run the BCFW recurrence, you're going to get things with weird intersections at the boundary. So the standard one is good. Well, like
the conjecture, or it's
I think it's essentially proved. I think this paper of Evan Zohar, McCracken, and Tesler looks at how they intersect when they were showing that they tile. I think they were looking exactly at how facets came together. Yeah.
Oh, yeah. Well,
I have a question.
Yes, Nima?
Oh, sorry. Go ahead. I just wanted to see that you can actually hear me this time. Sorry. Please go ahead with the other question. Apologies.
Well, maybe you better talk now while we can hear you.
Okay. Thanks. I have two questions. One of them is that cyclic polytopes are kind of special in being extremal. In the sense of maximizing the number of faces given a number of vertices. Is anything like this known about the Amplituhedron for any m? Are they extremal if we compare to other possible Grassmann polytopes? I guess those Grassmann polytopes are better understood now for m equals 1. I don't know what's known about m equals 2 even, but is there any extremality statement of this sort yet known for the Amplituhedron?
Oh, that's a really nice question. I haven't thought about that, but I would imagine we could figure that out for m equals 1 and 2 without too much trouble. Yeah, when you first started asking, I was just wondering in what sea of objects you wanted to place the amplituhedron.
Yeah, but I guess all Grassmann polytopes for a given
Right.
M.
Right. So you mean like all images of positroid cells?
Right. So long as, you know, there's some condition, I forget, Thomas defined for when the C dot Z map is good, is well defined, lands you in G K plus M. But once that's satisfied, yeah, that set of objects.
Okay, maybe, so you're talking about relaxing the condition on Z.
Yes. Relaxing
As
the condition on the Zs, and but of course keeping the Z so that the C dot Z map is well defined. So
Right.
those are Grassmann polytopes. So so in the zoo of all Grassmann polytopes, are amplituhedra extremal in the same way that cyclic polytopes are extremal.
Yeah, that seems like a very reasonable conjecture, but I don't know offhand. Yeah.
And a second quick question about the magic numbers. You know, as you know better than I do, understanding higher M amplituhedra would be completely fascinating. They're crazy, wonderful objects, but there is already a clue just in the tiling numbers for something that might be very important for whatever the quote unquote physical interpretation of these things might be. Already for M equals 4, the fact that you get Narayana numbers, and the fact that we know that Narayana numbers, in addition to having these cool symmetries that you talked about, at least some of the symmetries are obvious, like the parity one. They satisfy they satisfy recursion relations themselves. Like the Catalan numbers do. That the higher Catalan numbers, higher Narayana numbers are sums of products of pairs of lower ones. Is anything, and of course that's a deep clue to the underlying physics of factorization, and that's what goes into the BCFW recurrence. Is anything known about whether these magic numbers for higher M in general, whether they have this kind of splitting property, whether they satisfy recursion relations of this sort?
Yeah. So we've talked with you some time ago about this, and there's nothing so obvious that seems to be true for the next M, like M equals 6, but there is still some really nice combinatorics of maybe Baxter permutation. There is some nice numerology again, so there's a hope, but I think, I'm not so sure about the factorization though. That didn't look like it was happening, but I could be wrong.
All right, thank you very much. Thank you.
Thanks.
Yeah. Oh, actually, I have a comment before this on Nima's earlier question. So in my work with Elena on the M equals 1 grasstopes, actually, we found that those grasstopes are also regions of a hyperplane arrangement, and the amplituhedron for M equals 1 minimizes the number of regions.
Oh, okay. Oh, that's great. So that's a kind of okay, so it is seeing the amplituhedron as an extremal. Okay, because you guys exactly relaxed the condition on Z, and you're saying that the amplituhedron minimized the number of regions, like the number of tiles, say. Okay, that's great, thank you.
Cool, thank you.
And then actually, I had a question about whether you've computed anything for M equals 6, even just one example of at any point of a tiling or.
Right. So yeah, so maybe now a couple of years back, and also with Nima, we were visiting and we were looking at M equals 6, and actually there's this sort of weird phenomena where you see a kind of a fractional tiling for M equals 6. I forget exactly the parameters on K and N. Maybe it was like K is 2 and N is 12 or something, but it was this crazy example where we had to work really hard. Then we found like this fractional tiling, but sort of miraculously, that number of tiles was the magic number. So anyway, so something seems to be working, but it's a lot more subtle for higher M.
Okay, so let's
if I remember.
You can hear me, right?
Apologies.
Nima, can you hear me? Let's just go on break, come back at 11:30, and if you have more questions, we'll be here. Thank you so much.